Hello physicists, welcome back from break. Today we're going to talk about magnetic forces. So already this year we've talked about electric forces, which require us to have an electric field. We've talked about how to use those electric forces in circuits. And now we're going to talk about magnetic fields and magnetic forces. Okay? Now, most of the challenge of this new topic is that our magnetic force does not pull in the same direction as the magnetic field. So we've got that cross product in there, and we're going to have to learn how to use our right-hand rules. And this has some very interesting effects. In class today, in person, we're going to look at a electron that gets bent into a helix. Right here. So for instance, these coils are applying a non-zero magnetic field, and they cause the electrons, as they're spat out of this little tin can, to get curved. So we're going to talk about that today as well. Now, magnetism is of course, an ancient phenomena. People have known about it forever, ever since they discovered lodestones. In the same way that people have known about electric forces for a long time, ever since they saw, little particles jumping up to a piece of rubbed amber. However, it took a long time, till 1820, just 200 years ago, before there was a sort of a systematic discovery that the electric effects and magnetic effects are part of the same underlying system. Okay, so back in the day, it's easy to take a bar magnet, for instance, or a lodestone or whatever, and then you take some iron filings and you sprinkle them about, and they jump into a configuration that makes you think, oh, there's something out here. Okay, so this suggests already a magnetic field, but it wasn't until Hans Christian Ørsted he was setting up actually a class demonstration, and believe it or not, in 1820 they did have pretty good batteries, despite the fact that they didn't really know how they worked yet. And what they would do is it was called a voltaic pile. There's a lot of interesting history where Volta and Galvini had a big fights because they used these batteries to make a dissected frog's legs jump, for instance. And so they thought that it had something to do with animal magnetism and blah, blah, blah. They fought for decades, and it all turned out to be sort of irrelevant in the end. But here's where we had a big breakthrough. Ørsted took this big battery, and he was connecting it up so that he could run a current through it. So Ørsted in 1820 basically knew everything you know, if you've just been following this class, because they already knew how to use batteries, they knew how to work with currents. And what he discovered is that when he brought a compass close to that battery, it would deflect. So people already knew how to use compasses because they would use them for navigation. The compass needle points north. But what he found is that he could get that compass needle to go perpendicular to the direction of the current running through the wire when he brought it close to the wire. So there must be some kind of connection between magnetism and current. So in the next couple lectures, we're going to probe what that connection exactly is. And this discovery led to a huge outpouring of interest and research in this topic, including our man Faraday, and who, as I've said before, is the physicist you should love if you don't like math but are interested in physics, because he was a great experimenter who, he measured things quantitatively, but he did not do a lot of mathematical analysis. Here he's holding a bar because he realized that if you apply a magnetic field within a material, you can cause light that goes through it. You can cause the plane of polarization to rotate. Okay, so he was very interested in this. He discovered many of the magnetic and electrical phenomena that we are going to learn about in this class. And all of this kind of background empirical research was put together by James Clerk Maxwell, who sort of took together all of these experimental findings from many years and put them together in a system that you still learn about in physics class today. It wasn't the end of the story, but it was a pretty amazing feat of theoretical physics. So this rule is in secret. This is Coulomb's law. This rule is Gauss's law for magnetism. This rule is secretly Ampere's law, and then the only extra piece that Mr. Maxwell put in was this, but it was enough. It was a lot. Okay, so we're going to learn about all those in the next weeks. Now, the magnetic field has a new type of units on it, and we'll figure out what those units are in a minute. We call them units of Tesla, just like the electric field has units of newtons per coulomb or volts per meter. You know, there's many ways to say it. Tesla is kind of weird because look at this. The magnetic field and the magnetic force are very funny in that the magnetic field only applies to charges that are moving. Let me say that again. If you have a charge that's totally static, the magnetic field does not act on it. So that's unusual. And it's different from the electric field, right? So here's your electric field. Your electric field points in, if you have a positive charge, your electric field points in the direction of the force that the field applies to a charge. Okay? So this force over Q, this is newtons over coulombs. That was our units on the electric field. But now, with this magnetic field, we have something that the force is proportional both to the charge and to its velocity. Okay? In fact, it's going to be dependent on the cross product of the velocity and the magnetic field. But if we're just looking at the units here, it's newtons over coulombs times meters per second. So that's 1 Tesla. Now, of course, if you want to get fancy about it, you can play with this, right? And you find that a newton is a kilogram meter per second squared. If you put 1 over coulombs times meters per second, you end up with something like kilograms, and then the meters cancels out. Kilograms per coulombs times seconds. Okay, so it's a little bit of a weird unit. It's hard to wrap your mind around exactly what's going on there. Notice I was canceling out this as well, and so that kilograms over coulombs over seconds is a Tesla. Now, the reason why magnetic forces are weird is that the magnetic force depends on the cross product of the velocity of the particle and the magnetic field vector. Okay, so let's pause a little bit and think about this. Now, here I want to show you how it should be. Here we have foreign currency with the right-hand rule on it. I can't imagine this happening in the United States, but I like the idea. I like it. Okay, maybe maybe the next quarter can have the right-hand rule on it. So I want everyone to get their right hand out while you're watching this. The right-hand rule can help us to figure out the direction of magnetic force. So let's, for our first application, let's pretend we have a positively charged particle, and it's inside of a magnetic field. So our magnetic field we denote with the letter B. It has some direction. It's a vector quantity. Physicists would say pseudo-vector, but let's not worry about that right now. The V is the velocity of the particle that's going into the magnetic field. So, of course, that could be a current. You could have that velocity be of an electron in a wire, for instance. Okay, and that's in fact what we're going to do in lab this week. So, how do you find the direction of the magnetic force? Your index finger of your right hand is the direction of V. Your middle finger of your right hand is going to be the direction of B, and then your thumb is going to point in the direction of the force. So V cross B gives you the direction of the force. Now notice these two actually don't have to be parallel. They can just be in any configuration. They could even be anti-parallel like this, but the point is that your thumb is perpendicular to both of those. And I should just mention, if you have two vectors, A cross B, and they're in 3 dimensions, you don't actually have to use the thumb thing, okay? You could have your AX, AY, AZ, BX, BY, BZ, and this is just a shorthand for remembering using the determinant. And then basically you could say that the cross product is I times AY BZ minus AZ BY, and then J plus. So this is all in kind of the nice calculus 3 vector notation. So you'd have AZ BX minus AXBZ, and then K, that's your Z direction vector. You'd have your AXBY minus AYBX. So look, you could, if you're interested in just doing the math and cranking it out, you could do that. We're not going to do that in this course, but that cross product of V and B, you can do this all just with algebra if you want to. We're not going to do that in this course, but you could. Now, the other subtlety here. So I'm showing here. Here's a picture of the other way. If you want, you can go V cross B equals F. You could also go V cross B and then curl your fingers in the direction of B, and then your thumb would be in the direction of F. That's another way to do the right-hand rule. You see both of them. The only extra piece of subtlety here is that the force, that FB equals Q times V cross B. So if this Q is negative, that force is actually opposite the direction of your thumb when you do the V cross B thing. Okay, so that's a little bit tricky to think about, but let's try some examples and see if we can get the right answer. Okay, so let's look at A first. What is the direction of the magnetic force? So in each case, our force is going to be Q times V cross B, right? So get your right hand out. In our first picture, A, we're going to have V cross B, and then our thumb is pointing in the direction of plus Z, okay? And since this is a positively charged particle, for A, I should get a force in the plus Z direction. Okay, let's see. For B, if I go V cross B, V is my index finger, B is my middle finger, I should have my thumb then going in the direction of plus X, but it's a negative charge, so my force will actually be opposite that, so it'd be in minus X direction. Okay, now let's try another one. V cross B. Now notice these are opposite each other. Okay, and if we look at the cross product just in magnitude form, the magnitude of that force of B is going to be Q, V, B, and then it's going to be the cross product, so it's going to be the sine of the angle between the two. So for these, sine of 90 is 1. Sine of 180, though, is 0. So if I have a particle that's moving parallel to B or anti-parallel to B, the force is actually 0. Okay, let's see if that's what I said it was going to be. Towards the positive z-axis. Yep. Whoops. Towards the minus x-axis, towards the negative x-axis, and then none. Cross product is 0. Okay, so it's important to actually get your hand out and try it. I know it looks kind of dorky, but it is worth your time. Now, the thing to notice here is that if you have a charge, it is not just independently acted on by the magnetic field or the electric field or the gravitational field. Okay, that particle may be acted on by all of those at the same time, and then the forces add like vectors. So here I've got this equation, is called the Lorentz force equation. You have the force of the electric field plus the force of the magnetic field. And typically these are not pointing in the same direction. Okay, so this is sort of like an F net. The force from the electric field and the force from the magnetic field could be even in opposite directions. In some cases, if your E is pointing this way and your B is pointing perpendicular, you can have cases where the electric and magnetic field have forces that cancel out. So observation 1 is that electric and magnetic fields add like vectors. Observation 2 is a little bit hard to understand, but it's that the magnetic field does not do work. Now that might sort of stick in your craw a little bit, especially once we get to seeing how electromagnets can drag cars around in a junkyard and stuff like that. But essentially, what's happening in these cases is that when the magnetic field appears to do work, it's because it's changing into an electric field. Okay, so let's stave that off for a minute. The reason why this equation seems to say that the magnetic field does no work is that the work done has to do with the dot product of the force times the displacement. Okay, now that displacement is always, the only way you can get a work is to have the force to be effectively partially in the direction of the displacement. But magnetic force is always perpendicular to the direction of the displacement, and so you're not getting any work out of it. It's only changing the direction of your particle. Okay, so that's a little bit weird to think about. Now, another observation is that we've also learned about the force of gravity, F equals mg, and the charged particles typically, in addition to having this Q, that electric charge in coulombs, they also have some mass in kilograms. So if you wanted to get the total force from the electric field, the magnetic field, and the gravitational field, you'd have to add together those three vectors. Okay, So let's do a quick example and see how this works. Here's a homework example. I'm going to set it up. I'm not going to go through to the end, but I'm going to show you how to think about it. It says a particle of mass 10 grams and charge 80 microcoulombs. Okay, so they give us the mass, which is 0.010 kilograms. Remember, I'm going to try to use good units. And they give me the charge. The charge is Q. So that's 80 times 10 to the minus 6. That's what micro means. Coulombs. Okay, it moves through a uniform magnetic field in a region where the free fall acceleration is 10 meters per second squared. Okay, so that's our G. Minus 9.8 meters per second squared, or newtons per kilogram. Either way is fine. J had it, so that it's pointing in the minus y direction. Okay. So it says the velocity of the particle is a constant 20 I kilometers per second. Okay, so V is big. V is going to be 20 kilometers per second, so 20 times 10 to the third meters per second in the I direction, which is perpendicular to the magnetic field. What then is the magnetic field? Okay, so what are we looking for here? We are going to be looking for B. And the reason they told us that the particle is moving perpendicular to the magnetic field is that this cross product, remember, is V times B times the sine of the angle between the two. Okay, so if it's perpendicular, that means the angle is 90, and this just becomes Q times V times B in its magnitude. Now let's draw this out a little bit more. So here's our I, and there's our J, and there's our particle. Okay, our particle is moving like this in the I hat direction. There's its V. And it has a positive charge. Okay, so that's nice. Plus charge. And it tells us that the gravitational field is pulling in the minus y, so that's exactly what we're used to. So here's our force of gravity. Now, I just want you to think about this. It says the velocity of the particle is a constant. If the velocity of the particle is constant, what's the acceleration? If your velocity is constant, your acceleration is 0. So in this case, since our acceleration is 0, it means our net force has to be 0, and that force of gravity pulling down has to be contravened by a force of magnetism pulling up. Okay, so we know the direction of this force. So there's our FB. Now, we know that V cross B gives us that force of B. So I want you to try it. If your index finger is going in the direction of V, what direction does your middle finger of your right hand have to be pointing in to get you the force of B pointing up? Well, the way that I've drawn it, the B would have to be pointing into the screen. Okay, so B points into screen. All right. And if we want to find out what the magnitude of B is, now we could go ahead and set up this mg equals qv times b. And remember, I can forget about the angle because it's sine of 90, which is just 1. So I would set this up, mg equals Q, V, B, and then you can just solve for B. You have M, you have G. Make sure that you put in, since I'm writing this in terms of vectors, let's make sure you put in positive numbers in all of these cases. B is in fact going to be in the minus K hat direction into the screen. But you can now just plug in all of these numbers and find a magnitude for B. And the units on B will be in Tesla. Okay? So you can work that out the rest of the way for your homework, but I think I've given you a more than adequate start on that. Now, in class today, the next thing that I did was show an apparatus where an electron shoots out and gets bent into a circle by a magnetic field. Okay, so so in class we would we're going to look at the actual physical setup of this, where you can use a magnetic field to bend an electron around in a ring. Now, because last semester we talked about centripetal acceleration, and we found out that if you bend an any particle into a circle, it doesn't have to be an electron, it could be in fact a planet. That's where we used this before for Newton's law of gravitation. Bless me. Okay, the centripetal acceleration is related to the speed that the object is going around the circle. Okay, so it's equal to v squared, v being the speed that an object is going around, over r. Okay, and since you can do this, and in fact we can control the magnetic field that we apply, we can also control the radius. And the interesting usual application of this is that it gives you the mass to charge ratio, the m over q of the electron. So just to walk through this a little bit more gently, okay? Let's say that we have a particle that's in a magnetic field and it's being pulled into a circle. Okay, so here we're going in some direction. V cross B will give us our V cross B would give us our F. So in this case, our F would have to be towards the center of the circle. And let's pretend for a second that this is a positive charge, even though an electron is a negative charge. Just it makes it a little bit easier to think it through. But V cross B is F. So B would be into the page. And sometimes the way that we draw this in physics is with a little x. And the idea there is that out of page looks like the tip of an arrow coming out at you. So we draw that with like a little dot. And into the page, you think of that as like the crosshatch, the feathers of the arrow going in. And so we draw that like that. Okay, but if you don't remember that notation, that's okay. Okay, so what's happening here? Force is towards the center of the circle. We're going to use F equals ma. Okay, that's our Newton's second law. And that's really how we know that a force is being applied, because it causes some sort of acceleration. If we have an acceleration that's towards the center of the circle all the time, we can say that this is m v squared over r. Okay, that net force is a centripetal force in this case. Let's not worry about the electric forces. Let's say that the electric field is 0 in this region. Then what we would do is notice if V and B are perpendicular, this is just Q times V times B. Okay, so we just go force is this, Q times V times B. Okay, and notice that's our first equation. It's just F equals ma. Okay, so our magnetic force equals mass times acceleration. That's what this first equation is. Then the second equation I showed you is just solving this for R. Okay, so that actually is just algebra because we have V on both sides. I can divide both sides by V. QB equals mV over R, and then I can just solve for R. R equals mv over QB. Okay, so these are the two equations that I threw up on the last slide, and let's make sure that's what I got. mv over QB, mv over QB. Okay, so there we are. Now let's quickly do a problem just to make sure we understand how this works. Okay, so it says an electron of kinetic energy 300 electron volts. Now this unit of energy might be a little abstruse to you, but the reason why we like electron volts is because if you take a little filament and you put a voltage, like with a battery, of 300 volts and accelerate the electron through that 300 volts, the amount of energy it gets is 300 electron volts. An electron volt can be converted to joules. So an electron volt is a very small amount of energy. It's 10 to the minus 19th joules. 1.602 times 10 to the minus 19th joules is 1 electron volt. And it says an electron of this with this amount of kinetic energy circles in a plane perpendicular to a uniform magnetic field. The radius of orbis is 25 centimeters. Find the electron's speed, the electron's magnetic field, the motion, the circling frequency, and the period of motion. Okay, so let's actually work this out and get some numbers on it. Okay, so in this case, let's just go through it step by step. Okay, first we want to find the electron's speed. Okay, so how would we do that? Well, I would use 1/2 mv squared. The kinetic energy is equal to that 300 eV. But I would want to go ahead and convert that EV into joules so that I have good control over all of this. So let's go ahead and remind ourselves 1.602 times 10 to the minus 19th joules is 1 electron volt. So 1 electron volt is 1.602 times 10 to the minus 19th joules. Let me check that number again. 1.602 times 10 to the minus 19th joules. Okay. All right. And so now I have this in joules, and I can go ahead and find my V squared equals 2 times 300 eV. And I'm going to divide this now by the mass of the electron. So the mass of the electron is what? The mass of the electron is 9.109 times 10 to the minus 31 kilograms. Okay, 9.109 times 10 to the minus 31 kilograms. Okay, and so I took it times 2 divided by m, and then I have 1.602 times 10 to the minus 19th joules, and there's my 1 EV. My EVs cancel out. Joules over kilograms gives me meters squared over seconds squared, and then I can take the square root of both sides. Okay? And that's where I get this number, 1.03 times 10 to the 7th meters per second. Now you might think to yourself, oh my God, that's a huge number. And it is a big number. It's really fast. But it turns out it's not really close to the speed of light. Light moves about 3 times 10 to the 9th meters per second. So this is less than 1% of the speed of light. So we don't have to start worrying about relativity or anything. All right, now part B of this is going to ask, find the magnetic field magnitude. Okay, so how would I do that? Well, if it turns out that my object is moving perpendicular to an magnetic field and it's moving in a circle, I can use this same equation that I found before. So R equals mv over qb. R equals mv over qb. Okay, so I can stick in B equals Q times R over B equals, let me be a little more careful here. B equals mv over q r. Okay, there we are. Okay, so what would I need to use for the mass? I'm going to again use the mass of the electron. So 9.109 times 10 to the minus 31 kilograms. What would I use for V? I'd use this 1.03 times 10 to the 7th meters per second. What would I use for Q? Well, I would have to use my my fundamental charge. Let's see if I put that on this slide. I did not. So I didn't, but you might notice that this number here, this 1.602 times 10 to the minus 19th joules per electron volt, that is actually also not coincidentally the number of the amount of charge in an electron. So that 1.602 times 10 to the minus 19th coulombs is the amount of charge in an electron. It's because the a joule is a volt is a joule per coulomb, and so if you take joules times the electron charge, volts times the electron charge, it gives you electron volts. Okay, so anyway, and then for our last part here, for our R, we would need to put in that 25 centimeters, or 0.25 meters. Okay, and so that's where I'm getting the size in Tesla. So that's the answer that I'm getting. Then for part C of this problem, it asks what is the circling frequency. So that's how often does it go around the circle. Now to find this, all you would need to do is take the speed of the particle and divide it by 2 pi r. How fast it's going divided by how big the circle is. Okay, so that would give you something in effectively going from meters per second to times around the circle per second. It's essentially a unit conversion. Okay, and so in this case it would be that 1.03 times 10 to the 7th meters per second, and then over 2 pi times 0.25 meters. Okay, and that gives you this. Hertz is actually units of 1 over seconds. It's how many times around the circle per second. And then if you wanted to find the period of the motion, how long it takes to go around once, you just take 1 over the frequency. Okay, so it should give you something around 10 to the minus 7 seconds or something like that. Okay, so you take 1 over that and it'll give you an answer in seconds. All right, so that's quite a bit of work. I did give you a homework problem that's somewhat like this. In this problem, what you do is it says you have a initial potential difference of 1 kilovolt. Okay, so this is 1,000 volts. Enters the gap between 2 parallel plates having a separation of 20 millimeters. Okay, so this is going to be 20 millimeters. So that's 0. Take 20 divided by 1,000. Gives you 0.02 meters. 20 millimeters. 20 divided by 1,000. We're going to move this over 3 places. And a potential difference of 100 volts. Okay, so this is 100 volts. It says the lower plate is at the lower potential. Okay, what does that mean? That means that our electric field is pointing in this direction. Whoops. It says neglect fringing and assume that the electron's velocity vector is perpendicular to the electric field vector between the plates. In unit vector notation, what uniform magnetic field allows the electron to travel in a straight line in the gap? Okay. Well, this is kind of an interesting problem. Now notice we have a couple of different things. Part A is find the speed of that electron. Okay, how would you do that? Well, if you have an electron go through this gap, it would give you 1,000 electron volts. Right? It's an electron going through 1,000 volts. The energy gain would be electron volts. So 1,000 electron volts, you're going to convert that into joules, and then you're going to go 1/2 mv squared equals that number of joules. Okay, so that's just like we did in the last problem. Now then the second part says, look, you've got this 100 volts and the distance between them is 0.02 meters. So, what you would want to do is find the force of the electric field. So, how would you do that? Well, first you'd find the electric field is going to give you 100 volts. The size of that is going to be the change in voltage over the change in meters. So, 100 volts over 0.02 meters. Okay, then you could find the size of the electric force on the electron by going ahead and taking E, the electron charge, times E, big E, the electric field strength. Then finally you could go ahead and you're going to realize that in this case, if your E is pointing in this way, it's a negative charge, okay? The force on the magnetic field is pointing that way. And in fact, it's a little more confusing than it needs to be, but I'll set it up just so you can see the idea. The force of the electric field is pointing opposite because Q is negative. So your force of the magnetic field has to be pointing down. Why do I know that? I know it because the electron is traveling in a straight line in the gap, so it's not accelerating up or down. So the electric force is balanced out by the magnetic force. So you set Fe equal to Fb. Okay, so essentially you're saying E times the electric field strength is E times V times B. You solve for B in Tesla, and then I'm going to let you think about, should the magnetic field be pointing out of the page or into the page? Okay, so we can talk about that next time, but that's essentially the question. So there's a lot of physics in this. It might seem like we've made a big jump. In lab this week, we're going to be looking at electric forces, magnetic forces in sort of a circuit. And what we're essentially going to be doing is, if you look at this, what it is we have a battery, a voltage source, and we're going to have a big copper wire. Okay, and when we put that copper wire on a scale, it has some weight. Now, if I don't have any current running through that copper wire, there's no V cross B. The electrons are not moving in any particular net direction through that wire. So there's no magnetic force. However, when I turn the battery on, the presence of this horseshoe magnet, which I'm just going to have sitting on your table, is going to lift that bar up a bit. And because it lifts the bar up a bit, the number on the scale gets a bit smaller. And so the difference between the initial reading and the final reading gives you effectively a measure of how much force that magnet is putting on. So we're going to essentially measure how magnetic force changes with electric current. Okay, so we're going to connect all this stuff together in lab this week. It should be hopefully kind of fun. Okay, so I know that's a lot for one day, but we'll come back to it and we'll try to do it over and over again so that by the end of this unit we're not feeling too uncomfortable with it. So, what's weird about it? Magnetic forces depend on the magnitude, the magnetic field strength, and the velocity of the charged particle. Magnetic forces don't do work because they're always changing the direction of the particle. Okay, and finally, when you do these types of problems, sometimes the reason it's tricky is because you're thinking about multiple types of forces acting on the same particle: gravitational forces, electric forces, and magnetic forces. Forces that are acting on a particle in the presence of a gravitational, electric, or magnetic field. Okay? So thanks for watching, and don't get discouraged about this.